My name is Siddhartha, and I'm a PhD student at IISc in Bangalore. So we will meet every week once to do some problem solving. So to start with, this course is 12 weeks long, and today we are going to solve problems concerning week 1 only. So if there is anybody who is new to NPTEL, uh, the purpose of this problem solving session is to enable you to solve the homeworks, to solve the quizzes. So we do it week by week. So far, I think the contents for the first 2 weeks are uploaded. So the expectation is that you will see the videos of the current week, and then we can have a fruitful discussion, and you can take part actively in this problem solving session. So if you have any questions about the purpose of this session, you can let me know. I hope there is nobody in the lobby right now. Okay. So fine, this is the reference book. So all the references and materials are in this web page. Additionally, I think there is a feature for asking questions. So if you have any questions in the middle of the week and you want to ask, so here you can go to Q&A, and in Q&A you can ask questions, and some team member will answer questions or somebody else. All right. So I'm getting this beep sound when somebody is arriving, and then that person is in the lobby and I have to admit that person. So this is not the ideal way. We'll fix it. So yeah, I was telling that using this Q&A option, you can ask questions and some team member or the other will answer the question. So I'll also be looking at the Q&A periodically. So is there anybody who has already asked a question in Q&A? So I saw 2 questions. Says, is there anybody in this meeting right now who has already asked a question on Q&A? All right, fine. So I'll answer those questions in my free time. So let's get started. We'll get started with the problem solving session. So the idea is this course was also offered last year, and every week there were assignments. So we look at those assignment questions and we'll try to solve them. And in the process, we'll get ourselves familiarized with the content. So what is the date? Today is okay. Today is 30th. So this is session 1. Okay. So I had at least picked 1 or 2 questions. Okay, so even before that, if you have any questions regarding week 1 content, you can ask me. Then we can jump into the problem solving session. Are there any questions before we start? Okay. Okay, so I'll let you read the question. So everybody is familiar with the vertex cover problem. Okay, for those of you who are not familiar with the vertex cover problem, uh, so the goal in the vertex cover problem. So first of all, what is the input? The input is a graph G consisting of a vertex at E and an edge set, a vertex at V and an edge at E. And the goal in the vertex cover problem is to pick a subset U of B such that every edge is covered. Okay. So what does it mean? Such that for every edge in the graph. So what is an edge? Edge is a connection between two vertices. So let us say edge E is the connection between small u and small v. So for every edge u comma v, either u or v or both of u and v are in u. So that is the intersection of uv, u and v with the set that you have picked must be non-empty. So for every edge you should have covered it. You should have picked at least one vertex for that edge. Okay. So here there is an additional parameter k equals to 3. So the question that is being asked, so in parameterized algorithms, additionally to the input we are given a parameter, integer parameter. So here the meaning is, the question being asked is, in this graph, does there exist a vertex cover of size 3? So that means, can you pick 3 vertices such that all the edges get covered? So that is the question. Now, you can do that manually, like this is a small graph. You can check for all. So how many vertices are there? I don't know, maybe there are, I don't know. So 10 vertices, you can check for all 10, choose 3 possibilities, and you can answer me that whether it has a vertex cover of size 3. But that is not the purpose of the question. The purpose of the question is to run the polynomial time algorithm which is discussed in this lecture. So if you have not seen the lecture, I encourage you to see this lecture after this session. So the algorithm that is described in this lecture is being run through on this graph. Okay. And finally, as part of the algorithm, the 3 sets called crown, head, and body are constructed. So this construction of these 3 sets of vertices is called the crown decomposition, which is described in this lecture. And the question is, what is the correct crown decomposition for this graph and this parameter k? Okay. So even if you have not watched the video, you can still try this. We'll try this together. So you are given the steps that you have to perform. Okay. So what is the first step? So the first step is to find maximal matching. Okay. So what is a matching? A matching is a set of disjoint edges. The matching is a set of disjoint edges, and a maximal matching is a matching for which adding another edge into the matching will destroy the matching property. Okay. So a maximal matching is to be found. So in this figure, they're saying that the blue edges form a maximal matching for this graph. Let us verify it. So what are the blue edges? D, E, F, G, and PQ. So clearly these edges are disjoint. So there is no vertex which is common to two of these edges. So they form a matching for sure. Now, do they also form a maximal matching? So if you can find another edge which is disjoint from all these three edges, then you can conclude that this matching is not maximal. But can we find such an edge?
And how to find such an edge? Do we need to find the edges which are or the set of the disjoint edges in such a way so that the count is more than three, or what?
No, so the algorithm is saying that find a maximal matching. Now, the algorithm uh, implemented on this graph has found this matching, and the claim is this is already a maximal matching. So I am asking you that manually, do you see that this is a maximal matching? There is somebody. Okay, Aman. I have identified Aman. Yeah, so let's get back to the question. So your question, what is the question that?
Like here, I can find another matching, like say EF and then DB, uh, and then GR, and then QC. I'm going to repeat the release. So it is DA, EF, GB, and QC. So I found the set of the edges which are disjoint, and the count is greater than 3.
So you're saying that there is a matching of size 4. That's what you're saying.
Yes.
Okay, well, that is fine. That is probably fine. No, I mean, that is definitely fine. So the algorithm, if you see, it only asks you find a maximal matching. So maximal means another edge cannot be added on top of these existing edges. So it is already like saturated. So if you say that there is a larger matching, then I can agree that okay, that is so the maximum among all maximal matchings is the ultimate maximum. But the algorithm does not insist on finding the largest matching.
Okay. Okay.
So there could be a matching of size 4 as well. So a size 4 matching is possible. But whether this matching of blue edges can be augmented, that is the question. If you can augment this matching, means without discarding these three blue edges, then we will say this is not maximal. But it turns out that in this case, this is also a maximal matching because addition of any other edge will destroy the matching property. So what matching property is, the edges have to be disjoint. So now X be the set of vertices saturated by this matching. So saturated by this matching means you take every endpoint of the edges in the matching. So these endpoints are said to be saturated by the matching. So that is the definition of the set X. So this is all part of the algorithm. So we are just running the algorithm. Okay.
So I have a query here that if I add an edge EF here in this set, then still, I mean, the edges are not going to be connected.
So if you add an edge EF,
Yes.
what happens?
So then I can, at the most, I can make a move from D to F, or I mean, but still the connectivity would be in what is that, G and Q is not there. So therefore, still one edge would remain disconnected only. So in fact, the definition of this maximal matching thing is not clear. What's the meaning of this augmentation thing here?
Okay, so your voice is not very clear.
Oh, I
Uh,
see. So
I could make out what you said, but it looks like that there is a lot of humming in the
oh,
voice.
oh, uh,
Uh,
is this
is it
slightly better? No? Or do I need to log in from a different system in case if something is wrong? So yeah, but my question is that the this maximal matching thing, this idea is not clear, like, especially
okay?
what's the meaning of the term augmentation here. So what if I add an edge EF here? So then also, I mean, these three edges would still remain disconnected only.
Oh, disconnected? No, no. I am saying disjoint,
So
not disconnected.
disjoint only. One that I mean, okay, okay, disjoint means so. In that case, if I pick any, I mean, even if I pick a single edge here, that will also be a maximal matching.
No, no. Single will not be maximum matching. So let us define maximum matching first.
Yes.
Okay. So first of all, two edges are said to be disjoint if they do not share endpoints. Okay. So two edges are disjoint if they don't share endpoints. Okay. Now, what is the maximal matching? A set of disjoint edges is called a maximal matching if adding another edge, let us say we name this set something. We say a set F of disjoint edges. We say set F of disjoint edges is a maximal matching if adding another edge to F will destroy the matching property. So what does matching property means? Matching property means the set of edges have to be disjoint. So a matching is a set of disjoint edges. Now, a set of disjoint edges will be called maximal if adding another edge will not be possible. Adding another edge will require you to take one of the vertices which is already participating in one of the matching edges.
Yes, it's clear now. Yeah.
So if you take only one edge, that is not maximal because you have the liberty to pick other edges as well while keeping it disjoint from the edge that you have taken. Right?
Yes.
So let's get back to what they are doing. So they have first constructed one maximal matching, which is nothing but EF, GF, and PQ. And now they're saying that, okay, all these endpoints of the matching, I'm going to call it the set X. Now, what is the rest of the vertices? What is X complement? X complement has to be an independent set. Why? So the claim is this rest of the vertices outside of X, they must form an independent set. So what is an independent set? Independent set means the set of vertices such that no two has an edge connecting them.
So what is the guarantee that the complement of X will always form an independent set? Because in case if we could have selected a different X, then how to show that the complement of X will always result into an independence?
Yes, we can show by contradiction. So suppose for a contradiction that the complement of X was not an independent set. So that means that there exists at least a pair of vertices having an edge between them.
Yes.
So that edge along with this matching will still be a matching of larger size, but that
Yes,
is not possible.
but larger in size is not the requirement for this maximal thing, because it is maximal and not the maximum.
So larger in size, that is the definition. Let us look at the definition. That if you can add another edge, then we cannot call it maximal. So adding an edge would not be possible to the existing matching if you want to call it maximal. I understand your confusion. So you are still thinking in terms of maximum and maximum. Let's do it with a small example. Let's try to do this with a small example. Uh, yeah, let's do it this way. So it's a smaller graph. So if you ask me that what is the maximum matching, then I will say that you should take AB and you should also take CD. That is a maximum matching, isn't it?
Yes.
There are only three edges. And if you take AB as well as CD, then of course you cannot take BC because BC will have B, which is already part of the matching, and C, which is already part of the matching. But if you take BC, that is also a matching. If you take only the edge BC, that is also a matching. And additionally, it is also a maximal matching. So BC alone forms a maximal matching. Because if you already take BC, then you cannot take AB and CD into the matching. So adding another edge will destroy the matching property. What is the matching property? That the edges should be disjoint. So if you take AB along with BC, then B is common. So disjointness is disturbed.
Yes. Yes. Clear. It is clear.
So now there could be many maximal matchings. So one of them is obtained by this algorithm. But whatever is the maximal matching, the rest of the vertices must form an independent set. Here also, if you see, if you take BC, A and D are independent. If you had taken A, B, and CD already, then the complement of ABCD is empty set. So empty set is by default independent.
Yes.
So that is the reason that X complement is an independent set. So these four vertices in this graph, A, B, C, and R are forming an independent set. So how the algorithm proceeds is, in the next step, it forms a bipartite graph between x and x complement. You know that x complement is only already independent. Sorry, so they're considering this bipartite graph between x and I, and here they're forming a maximum matching of these red edges. So with some effort, you can see that this is a maximum matching, that there cannot be a matching in this graph of size 4. And they obtain a vertex cover also of size 3. And then there is a way to sort of decompose the vertices into what is called crown decomposition. So it's a rule. So I have written down the rule. So this we will see.
And how the vertex cover is being found here?
So this is a bipartite graph between x and I. And if you take uh, so so in the algorithm, as you can see from, so there is a difference between this figure and this figure. So some of the edges they have deleted. For example, this edge EF they have deleted, and this matching, the previous matching edges they have deleted. So these matching edges are not there. EF has been deleted. So some rules that they have applied, which which can be understood only when you read this lecture, you watch this lecture. So after doing this reduction, after moving from this graph to this graph, it turns out that the edges, sorry, the vertex, this is an independent set as well as this is an independent set. So there are two independent sets. So you can always take one of the partitions and declare it a vertex cover. But you can apply a minimum vertex cover algorithm on the bipartite graph and obtain the minimum vertex cover as well. So that's what you have done. It's not immediately clear that why means how this has come to this, so which you can understand only after reading this, watching this lecture.
Mm.
So the point is how to do the crown decomposition. So the intermediate details are not uh, very. It's already, it's part of the question that after you have been given that, okay, this is the reduced graph, and this red vertices are the vertex cover. You have this X set and I set. Now, how do you do the crown decomposition? So the rule says that, so the crown decomposition rule is the following, that head of the crown is the vertices in S intersection X. So what is S? S is the minimum vertex cover. So what is S? S is this red vertices T, G, and C. Intersection, I mean X, so all these things D, E, F, G, P, and Q. So which two are common? T and G are common. This is the head of the crown. So that is the rule. S intersection X you have to compute. So what is a crown? So the neighbors along the matching M. the neighbors of head along the matching. So this this we're talking about this matching here in the second figure. Let's look at the figure and figure out what is the crown. So you have identified the head to be D and G. So D and G are your head. And now D is connected to A along the matching and G is connected to B along the matching. So matching are the red edges. So you know that D and G are your head. So D's connection along the matching is to A and G's connection along the matching is B. So that is why A and B are in the ground. That is the rule, going by the rule. And rest of the vertices are going to be in the body. So everything else. So let us mark, or maybe I'll just write down. So body is rest of the vertices. The remaining vertices, whatever. C, E, F, H. H is here. Let's see. Oh, H is not there. I mean, I'll just write B minus body minus ground. So all the vertices minus head minus ground. So once you have computed head and ground, the rest of the vertices are in the body. So what is the correct option?
The option is head is DG. So yeah, correct option is first one.
Yes.
DG and remaining one.
Yes, yes, yes. That is the correct one.
Yes. So my question is that can we find this maximum matching in the polynomial time?
Your voice is muffled.
Oh, I see. So can we find maximal matching in polynomial time?
Yes, yes, yes. In any graph, you can find the maximum matching in polynomial time. So the thing is, it's simple. So you have a graph and you pick an edge arbitrarily. So you have picked this edge. Now that you have picked this edge, you have decided to put it into the matching. You cannot take those edges which are incident to these two endpoints. So you cannot take this, you cannot take this, you cannot take this, and you cannot take this, right?
Yes.
Because that is the definition of matching. Matching definition says that you have to pick edges which are disjoint, vertex disjoint.
Yes.
So once you have picked this edge arbitrarily, you have to not pick, you have to discard and take a different color. So black is for taking, red is for discarding. So I must discard incident to the endpoints of the edge that you have picked. So now you are left with remaining graph. Again, in this remaining graph, you can pick an edge arbitrarily. So let us say you pick this edge. Now, if you pick this edge, you cannot take those edges which are incident to its endpoints. So you cannot pick these guys. Now this is a maximal matching because you have done it exhaustively. There is no way you can add, augment this matching, isn't it?
Yes. Yes.
So it is going to take order E time. That is time proportional to the number of edges.
And what is the purpose of this question? That we could identify an independent set present in a graph in the process of finding its vertex cover.
The purpose of this question is to uh, answer this question that whether this graph contains a vertex cover of size 3. But if you want
Yes.
to answer this question naively, then you will end up taking n to the power k time, where n is the number of vertices and k is the parameter, that is size of the vertex cover. But
Yes, but yeah, but in this process we could identify a small independent set as well.
you did, indeed, you could do that, yes. But that was a byproduct of the algorithm.
Okay.
So why so many things, so many complicated things is to reduce the runtime. So instead of taking n to the power k time, you want to take some function of k into n to the power constant time. Now, here k is only 3. So if you take sort of like k square n to the power c time, so you have 9 into n to the power c time. So it turns out that if c is 2 for you, so you can do it in 9 square time instead of n cube time. So the point is, with all this machinery, you can reduce the running time of finding the vertex cover.
Yes.
Is there anybody in the lobby? Let me check. So from next meeting, I will fix this issue that I have to manually admit people. So I can see right now there are 1, 2, 3, 4, 5, 6 participants. So this is the end of this question. Okay. So we'll move to the next question. Okay, so we'll look at the quiz. So this is the current offering of the course. I'll go to the previous offering. So this is the question we have solved. First question. So let's look at the second question. Okay, even if you see the answer doesn't matter, we have to justify the answer. So looking at the second question. So here you have been given an instance of the vertex cover problem. So that is a graph and a parameter k. So here k is 3. And we are running this 4 to the k n to the constant time algorithm, which is discussed in lecture 1. And the question is, uh, what is the output of the algorithm, whether it says yes or no. So the question is whether this graph contains a vertex cover of size 3. If yes, then the algorithm would say yes, otherwise no. So you give it a thought whether you can see a vertex cover of size 3.
So I think there is a one. Like say if I select the vertex A and B and H, then A, if I cover A and then B and one more, I would be requiring two more. So two more vertices. So I think that no, there does not exist the vertex cover of the size 3. I will be taking A and B for sure because these vertices are having highest degrees. I will cover maximum number of edges, and then if I choose G, so we'll cover only two. Yes, we require four vertices in this case.
Are you sure?
Yeah, I think I cannot find a vertex cover of the size 3 here. Um, However hard I try. G and then H. No, four is the answer.
Okay, so yeah, so there is a rule. So they have discussed an algorithm, or there's somebody on the lobby. Let me this person. Grub node saying, so I've admitted grub node. So why do you think that uh, ABH is not a vertex cover?
So initially I thought A, B, and H only, but then I saw that G, B is not getting covered. So yeah, and because this GB was not getting covered, so I'll have to include G as well.
No, you have taken B. B covers all the edges
Yeah,
incident to
B
B.
covers, yes, B covers GB, and oh yes, so AB and H is sufficient. Yeah, yeah. So yes, we have a vertex cover of this size too.
So you can just say yes, or you can do all this machinery. So let's do this. I will just, what I will do is I will show you how to get the answer according to the steps that they have given. Uh, so I won't be able to point anything. I'll just follow my words. So they're saying that look at this set of four vertices A, B, C, D. In this graph, AC and BD forms maximal matching. So what is the maximal matching? That another edge cannot be added to AC and BD, because if you do so, then the matching property will be destroyed. So now, once you have identified this maximal matching AC and BD, you know that the rest of the vertices forms an independent set. That is by the logic in the previous question. So EFGH forms an independent set, right?
Yes.
So now they are saying that, okay, uh, this four vertices A, B, C, D, call this set S, capital S, and the rest of the vertices is capital I. Now you try to take some subset of S, so they're calling it Y, and then, for example, you had taken ABH, so the subset that you had taken was A comma B. So from the neighborhood of S minus Y, Y is what you have taken AB. So S minus Y is C comma D. So what is neighborhood of C comma D? So this is open neighborhood symbol. That means you don't include yourself. So open neighborhood of C comma D is only H. So this must form a vertex cover. So there is a simpler way of looking at it. So AB you have taken, and CD is remaining, which is Y. Sorry, which is neighborhood of Y. I think I should make a copy of this figure and I'll show you. So they are saying that the way you can obtain a vertex cover is that you have identified this set. We call it S. So we have identified the set A, B, C, D. Now, in your case, you had chosen a subset Y of S, which was equal to A and B. Now, AB is responsible for covering uh, all the edges incident to them. So, including these kind of edges, which have gone outside this S. But how about this four things together is S. How about S minus Y? S minus Y CD. So you consider the neighborhood of S minus Y that is going into the independent set. So intersection the independent set, that is only H. Now H and AB together should form a vertex cover. So now you know that this vertex cover size is only 3. So ABH is a vertex cover. Let's go back to the question and now we'll see it again. So they're saying that check if Y union neighborhood of S minus Y intersection I is a vertex cover of size at most k. It turns out to be yes, and in our case k is 3, so that's why the answer is 3. But you can, instead of going through all these steps, you can also do it by looking at it. Any doubts on how to answer this question?
Yes, it's clear, except two things. That why the size of the S is less than or equals to 2k. Uh, and the second one is that even though it seems that this union and intersection thing will give a vertex cover, but how to ensure that it will always be less than or equals to k?
Cannot be ensured. You have to try all possible subsets. So, for example, you had tried only one subset AB. So now there are 2 to the power 4 subsets of S. So S is A, B, C, D, right? So let's go back.
Yes.
So S is A, B, C, D.
Mhm.
So you have to try all subsets in the power set, or rather all sets in the power set of S. So as possible Y. Now you are lucky. You have chosen Y to be A and B. So let us. So is it any? If you already take Y to be uh, so what do you what if you cannot take 5? So you want to check whether this quantity Y union this thing is a vertex cover. So you can take Y to be 5. You cannot take Y to be the entire set. So the entire set is AB. If you take A, B, C, and D as Y, then you are already taking 4 vertices into your vertex cover. You want to take only 3 vertices. So you should try 15 possibilities. So how many subsets do S have? 2 to the power 4. So out of which you have discarded this guy. And then you manually do it. Like for all possible Y's, you check what is this quantity, union this quantity. If it turns out to be less than equal to 3, then you will say yes. So that is the process.
Okay.
It is
Yeah, so
very clumsy.
there is a catch in this problem because we just found vertex cover. So seems to be a good mechanism because the mechanism which we are following we are finding the maximal matching, which we can get in the polynomial time. And after getting the maximal matching thing, then the remaining steps can easily be done because all this interaction and the union can again be done in the polynomial time. So it seems that we found the vertex cover in the polynomial time, or there is a catch in this problem, except that we need to explore
So
all possible subsets.
yeah, so that is the catch, that the running time will depend on what is the size of S. So you have to try all possible subsets of S. So you have how many cases? 2 to the power size of S. So now in this case, size of S is 4. So running time is sort of like 2 to the power 4. So if it were such that so since uh, so the running time is dependent, I'll write it down. So running time is 2 to the power S into some polynomial. So now what is the size of S is what matters to you. So it is uh, if you parameterize with the size of the maximal matching. So what is S? S is all the vertices saturated by the maximal matching. You know how to find the maximal matching quickly. So you have found S quickly. Now you have so many cases to consider. So if the maximal matching turns out to be small, then your running time will be small.
That is what we wanted in this FPT thing, to bring the complexity in this format, FK and then multiplied by n raised to the power c.
Correct.
Right.
Okay, so I have how many questions are there? 6 questions today. So these 2 questions are simpler. So in fact, you have to keep on applying rules. Like see, in the first 2 questions, you have applied all these rules, you have found a matching, then you have concluded that the remaining vertices are uh, an independent set, and then you have done this and that, and finally you have been able to tell that okay, this is a vertex cover or not. I mean, this admits a vertex cover of size 3 or not. So similar things we're going to do for the rest of the questions. So this again has dependence on the rules. So I'll let you read the third question. We can read the third question. In fact, we can take a 5 minutes break, and I will keep this open in front of you. So you can read both third, fourth, and fifth. Yeah, you can read the third and fourth only right now. And after 5 minutes, we will solve these questions. Okay, let's get back. So how many of you are familiar with the hitting set question? Anybody who knows what is the hitting set question?
No idea. Can you
Okay,
speak
so
it up?
I'll define. All right, let's define the hitting set question. So it is easier to see the hitting set question in the geometric setting. In fact, I'm offering a workshop on geometric algorithms, so I think I'll give you a geometric definition of hitting set first. So uh, let's try to use this example only. So there's a universe of points. So you are given some points on the Euclidean plane, on the 2D plane. We'll keep it very simple. So these are the points. This is part of the input. So this is also what we will call an universe. So universe consists of these points. Let's say P1 through some n points. And additionally, there are some sets. Okay, so the sets are defined by geometric shapes. So let us say, additionally, you know that there is this circle. It's not looking like a circle, it's draw a proper circle. Okay. So in addition to the points, you have some circles. Now observe that each circle contains some set of points. Right. So for example, let us first name these points so that it is easy to talk about them. So let us say I number these points 8, 9, 10, 11 points are there and there are 5 circles. So I'll say circle 1, circle 2, circle 3, circle 4 and circle 5. So circle 1 contains 4 points 1, 2, 3, 4. Circle 3 contains 4 points 3, 4, 5, 6. Circle 2 contains 3 points 4, 6, 7 and so on. So we'll say that a point hits a circle if the circle contains it. So that is the definition of hitting. What is the meaning of hitting? A, a point, why did I write points? No, a point. A point hits a circle if the circle contains it. So 1 hits circle 1, 2 also hits circle 1, but 3 hits circle 1 as well as circle 3, right? Because 3 is inside both these two, isn't it?
Yeah. Yes.
So the question is, so the hitting set question is, find the minimum number of points that hit all the objects, all the circles. That is the question.
So, like say, if since point number 3 is hitting to C1 and C3 both, so it may be, I mean, we can model this thing as a graph wherein 3 is a common endpoint of the edges, say to C1 and then C3 kind of, okay? And then we find the vertex over from that.
Okay. No, so I didn't get it. So what are the vertices of the graph you are forming?
So my point is that so like say vertices here would be so these many points will form the vertices, and since 3 is hitting to both C1 and C3, so this thing should be imbibed into an edge, and I
Correct.
don't know
So it
how
is
to do.
necessary to capture this detail that 3 is hitting both C1 and C3. So uh, the other ways, so if you only say that the points alone form the vertices of the graph, then it is difficult to capture this information regarding the overlap of the objects.
Yes, so better we take C1 as a vertex, and but again, then C1 comprises of so many points. So how to show this fact that 3 is connected to both C1 and C?
Yes, correct. So yeah, so this turns out to be an NP-hard problem, and there are approximation algorithms. But for the purpose of today's discussion, uh, we can see that so manually, let us say, which points shall you take? So if you take 6.6, you are taking care of three circles, C2, C3, C4. Okay. So now you only have to take one more point from C1 and one more point from C5. So we are sure that taking 3 points is definitely sufficient to hit all these 5 circles. But then the question arises whether 2 points will also suffice.
How to?
Sorry?
Yes, 4 is connected to 3 circles and 10 is connected to 1, 2, and yes, all have been covered here.
Yes. So 4 and 10 will also suffice to hit all these circles, isn't it? 4 is responsible for hitting circle 1, 2, and 3, and 10 is responsible for hitting circle 4 and circle 5. Then the question arises whether a single point will suffice. So whether there is a point which is common, which is contained within each of these 5 circles. That is not the case because we can see that these two circles are disjoint. There is no point between these two. So hitting circle 2, right? So now let's look at the question. So now instead of the geometric setting, you have this uh, set system setting. So this is a universe, and again you have a family of sets from the universe, and the question is whether you can pick 2 points from the universe, 2 elements from the universe that hits all of these sets. That is the question. That is the question. No, I mean, this question is different, but that is the meaning of the creating set in this context. And why creating set? Because every set, and I'll make a copy of this and I'll show you in the editor. So this is the set system. This is the set system. And you can think of these A, B, C, D as points in the geometric setting. And this set ABC means that there is a circle. There is a circle which contains A, B, and C. ABD means there is a circle that contains A, B, and D, and so on. And the question is, can you pick two of the elements such that all these sets are hit? So do you understand the equivalence?
So yeah. So I can take A here, and A is there in three subsets. So at least out of these six sets, three have been covered. And now I take F, and F is covering the remaining three. So A and F. So I require these two elements covering all the subsets.
Correct. So that is a valid hitting set for this family F. And oh, so why is it called the three hitting set problem? Three hitting set means every set in the family consists of at most three elements. So in this case, every set is consisting of exactly three elements. But the definition of three hitting set is every set in F should have at most three elements. So now you have found out to uh, find a hitting set for this instance, for this example. Now let's go back to the question. Okay, so the question says that look, in this video, lecture 4, there is a set of rules that are applied to this family, which sort of reduces the size of the instance. So finally, after applying all these rules, the question is the reduced instance has how many sets in the family? To answer these questions, you have to understand what are these rules RRA, RRB, and RRC. Right. So I'll write down the rules for you. So this is okay. So we know that you have already found, Mr. Goel has already found the hitting set. But the point in this question is, can you sort of reduce this instant into smaller instances and then extract out your solution? So that is like the nature of all these problems that we are seeing. But yeah, we'll go through them. So what is the rule A? RR means reduction rule. Okay. So the reduction rule, there's somebody, Kanimochi. I'm going to admit Kanimochi. Okay. So what is the first rule? RRA. If an element is not contained in any of the sets. So if an element is not contained in any of the sets, then it cannot hit anything. Then it is useless, right? If an element is not contained in any of the sets in F, then it, then it makes no sense. There is no way it can hit anything. So that is the first rule. So let us apply the first rule. Do you see an element which is not appearing anywhere?
So if an element is not containing any of the sets in F, so uh,
It's
all the
not
elements,
completely clear.
all the elements have been covered.
All the
All the elements have been covered. I mean, all the elements are the part of at least one set.
yes,
There
yes.
is
So this rule is not applicable.
yes.
Okay, so let's look at the second reduction rule. It says that if there is an element which is contained in k plus 1 sets. So what is k? Okay, let's look at the k is written here only. K is 2, right? So the question is whether there is a hitting set of size 2. So k is 2. So the rule says that if an element is contained in k plus 1 sets and uh, Okay, an element is not only contained in k plus one sets, or it is also common. Okay, so if an element is common to k plus one sets, then it is responsible for hitting all these k plus one sets. So you should take it. So formally, it has been written this way. If an element V is contained in k plus one sets, let us say the sets are named S1 through Sk plus 1, such that Si intersection Sj is equal to V for all I not equal to J. Then you should make a new set. Then what is the rule? Then make a new set consisting only of V and drop this K sets. Yeah, K plus 1 sets. S1 through Sk plus 1. Okay. We are going to see if this rule will be applicable in our setting. So let's scan this input. So what is this set intersection this set? It's only F. This set intersection this set is only F. This set intersection this set is also F. So all these three sets are capable of being hit by F. So we'll drop these three sets and write F instead of them. So that's the application of rule B. That is just F. F can hit all these three.
Yes,
Fine.
this makes sense. Yeah.
But then there is another rule. It's the same thing. I'll just copy it. See, if there are two elements which are common to many sets, then you make a set of these two elements and drop rest of the things. Okay. So it is like if this is rule 3. Oh, just a second. So I'm going to write rule C. This is as per the question. I mean, this is all common sense, but they have written it formally. So if the two elements, so if instead of and, just check which I'm saying the correct thing. If two elements, U comma P, are contained in so many sets, k plus 1 sets, such that their intersection, pairwise intersection consists of these two elements only. Okay, U and V only. Then you can take these two and remove, drop the rest of the things. So that is what is happening here. So you see these three sets. AB is common to all these three. So you can as well drop these three sets and replace them by AB. So this is the reduced instance. In the reduced instance, you have two sets, AB and F. And now you can apply the first rule. That's those elements which are not responsible for hitting any of the sets, which do not appear in any of the sets in the family, are useless, must be dropped. Okay, so you can see that other than AB and F, everything should be dropped.
Yes.
So after application of these two rules, we are now able to do it. But before that, it was not possible. So we will cut these things. Oh, please, there, sorry. So this is the final setup. After this, there is no reduction rule applicable. Now we go back to the question. The question says, we exhaustively apply rule A, rule B, and rule C discussed in module on lecture 4. The reduced instance has how many sets in the family? So in the family, there are two sets. A comma B is one set, the other set is F. So that is the reason the answer is 2. Is that fine?
So what is K here?
What is?
K is equal to 2. So what this 2 signifies here?
So the question is, does this set system, that is U and F, this is called the set system as well, contain a hitting set of size 2? In other words, can you pick two elements that hit all the sets in the family F?
Okay. Okay. So except kernelization, kind of a thing wherein we could reduce the problem size and uh, uh, so and wherein we could reduce the problem instances. What else is there in this problem and which makes this problem interesting?
This is just showing how cardinalization is done. This is just to judge the understanding of the student about cardinalization for this creating set problem.
Okay. Okay.
Okay, so the other next questions are quite easy. Uh, which one is the easiest? I think this one, fourth one is easiest. Yes, in this question. So what is okay? So here you are given a set of points and again an integer parameter k. So this is called the point line cover. So the question is, can you draw at most 3 lines, or let us say 3 lines on the plane, such that all these points are covered? That means at least one line passes through. For every point, there is one line that passes through it. So you are allowed to draw 3 lines, and you have to ensure that you have drawn at least one line passing over every point. Is the question clear? So for every point, you want to make sure that at least one line is passing through it.
So I can draw one line passing through 0, 0, 1, 1, 2, 2, and 3, 3, and the other line passing through 2, 2, 3, 1, and 4, 0, and one more line passing through 3, 1, 4, 2, and 5, 3. So I can draw 3 lines here. So what is the question? Right? So where do we have the reduced instance here? Reduction in
Yeah,
what
so
sense?
we have to now apply the reduction rule. So the question, so what is the point line cover is clear. That what is the question? Now, in this case, the question is, after you apply a certain reduction rule, what is the reduced instance? So I will first write down the reduction rule that they're referring to. So this is the reduction. First, let's copy this figure. This is your instance. The reduction rule is the following: that if there is a line L covering more than k points, then remove all points covered by L and reduce the parameter k by 1. So I'll write it down. If there exists a line L covering at least k points, oh, it's saying more than k, so at least k plus 1 points, more than k points, then remove all points covered by L and reduce the parameter k by 1. So that is the kernelization rule. Okay. So now what is your value of k? That is 3.
Yes. Yes.
So I think if this is the rule, so let's look at the answer. I think the rule is what is the answer? The answer is 1. Uh,
So 1 point from here and 1 point from here.
I think there should be 2 lines. So there is a problem. So I think so I think if you set equality, so if you say that I am going to allow a line to pass through k points also, then you can draw 2 lines. So you can draw this line and this line, and then you will be left with only 1 point. And that's how the answer is 1. But when I'm looking at the reduction rule in the video, it is showing that if there is a line L covering more than k points, but I do not see how you can cover 4 points by 2 lines. So first line you are drawing is this one. This is okay. So first line is this. You are covering 4 points. Now there is no way to cover the rest of the 4 points using one line, right?
Yes.
So I think.
But the value of k has also been reduced by 1.
Oh, right. K is also reduced by 1, right? Yeah, right. So this is correct. Thanks. So after you have taken this, sorry, after you have taken this line, this is a reduced instance, but k has been updated to 2. So now k plus 1 can take this thing. This is fine. So you understand that only 1 point will be left.
Yes.
Anybody who has a doubt? All right, so we'll move forward. We have about 25 minutes. We have about 2 questions. I think we'll finish well before time. So the clique problem. What is the clique problem? So this is your input. The question is, okay, parameter k equals 4. So the question is, does there exist a clique of size 4s in this graph? So that is, can you find 4 vertices in this graph that forms a complete graph, complete subgraph in this graph?
So, like in this case, we do not have a clique of the size 4 because we cannot find a subset of the 4 vertices wherein every vertex is connected to every other vertex. So, like here,
Correct.
we are not connected, so therefore we are clique of 4 is not there.
Yes, that is the right reasoning, and the answer is going to be no. But we have to follow this reduction techniques. So in this lecture, so there is a reduction rule which we are going to follow. Okay. Uh, so let's read the question. So we run the 2 to the delta g. Oh, what is delta g? So delta g is the maximum degree in a graph. So it is the uh, so what is the degree of a vertex? The degree of a vertex
Maximum,
is, yeah,
maximum number of the edges incident on that vertex. So, like
yes,
maximum degree here.
that is correct. So delta g is denoting the maximum degree of a vertex in this graph. So there is a way to find the clique in this running time, 2 to the delta g into n to the constant. And that algorithm is discussed in this lecture. So capital N of P is the open neighborhood of a vertex. That means it is a set of vertices to which this vertex P is connected via edges. So for every vertex, we have to check whether in its neighborhood there is a clique of size k minus 1. Because if that is the case, so let's copy this figure and then we will see. So this is the case. So how many vertices are there? There are 5 vertices. So what you have to do is for every vertex, we check if the neighborhood of V has a clique of size k minus 1. Because if that is the case, then along with V, it will form a clique of size k because V is connected to everybody in its neighborhood. That is the definition of neighborhood.
Yes.
So that's what you have to do. And then, so how many vertices are there? That is the first thing. There are 5 vertices. So first we check A. So in the neighborhood of A, there is only B. So not so A is not even connected to k minus 1 neighbors, that is 3 neighbors. So A is not going to participate in a clique of size 4. So forget A. B is only connected. Okay, so B is connected to 3 neighbors. But these 3 neighbors don't form a clique because this edge is missing, this edge is missing. Right. C is connected to how many neighbors? Again, 3 neighbors. B, D, and E. But they are not forming a clique of size 3. D is connected to 3 neighbors, E, C, and B, but they are even not forming a clique of size 3. E is only connected to 2 neighbors, so question of forming a clique among its neighbors of size 3 does not arise. So that is why we can conclude that this algorithm discussed in the video will say no. Fine.
So in this way, we can find the clique for any graph in the polynomial time. Like say, we require order of n time to scan through all the vertices and to check whether a clique is possible for its neighbor or not. We would again be requiring n square amount of the effort. So in total, n cube effort is required to know whether there exists a clique in the graph or not. So how
No,
can this be
so
possible?
if you give it a more thought, so they're also saying that the running time is not polynomial, but 2 to the delta G n to the constant. So let's write this running time. So 2 to the delta G. So delta G is your parameter n to the constant. This is going to be the running time. Now, what is the value of delta G you can expect? Can you expect a large delta G?
So unless the value of the delta G is not exponential,
Yes, yes. If you say that it is a degree bounded graph, that every vertex has constant degree, then there is a polynomial time algorithm.
so what are the reasons of considering that the maximum degree of a graph is not polynomial and may become exponential?
I didn't get you. Can you repeat?
Yes, so my point is that so why to consider this thing that the or there are why to consider this thing that the degree maximum degree of a graph may become exponential?
No, it cannot become exponential. It can become linear in n. So, for example, in a dense graph, it can so a dense graph has order n squared edges.
Yes, and order of
So,
yeah degree.
so the sum of degrees of the vertices. So I'm taking the sum of degrees. Okay. So maybe I'll just say degree of V is the number of neighbors of V. So for all V, that is also order n squared. Because for
Yes.
every edge you are counting 2 degrees.
Yes.
So now you know that there could be so there must but how many vertices you have? You have order n, you have n vertices. The number of vertices is only n, but sum of degrees is so much. So there must exist vertices with degree order n. Means order n
Yes.
squared by n. That is order n.
Yes. Yes.
So order n is the maximum degree you can expect in dense graphs. So that is the reason the running time for dense graphs in this for this algorithm will become exponential.
Yes. Clear.
So anyhow, the point is uh, uh, for the purpose of this question, the answer is no, that there does not exist a clique of size 4 in this graph. Now we have come to the last question of the day. I can also let you see the answer. So what is any clue what is the edge clique cover problem?
So do we need to age click is, I don't know, but could be that all the edges must have been covered. So we have to find what? Oh, I have no idea.
Yes, you are more or less correct. I will write down the formal definition from the book. Edge click cover. Yeah. So look at this question. You are given a graph G and a parameter which is an integer which is equal to 4. So the question is, let's draw this figure. So we are asking the edge click cover question. So the question is, does there exist k subgraphs h1 through hk of G such that each hi is a clique. Clique is a complete graph, and the union of the edges of these cliques is nothing but the edge set of the graph. So basically, it is not a disjoint partitioning of the vertices. So you are picking cliques. You're clicking subgraphs. You are picking subgraphs which are cliques, and these subgraphs together forms the graph, the entire graph. You're not leaving any edge out in the process. So let's look at this picture.
Is
So
the
for example,
repetition allowed?
sorry.
Is the repetition of the edges allowed while taking the union? I mean, is it possible that one edge becomes a part of the two
Yes,
independent peaks? Okay.
yes. So this is a clique of size 2. This is a clique of size 3. This is a clique of size 3. And this is a clique of size 2. So I can see that union of these 4 cliques will cover all the edges. I mean, yeah. So this is a triangle, another triangle, edge, edge, 4 cliques. So, but yeah, so the question is not this. The question is, after you apply the 2 reduction rules, RR1 and RR2, as described in this lecture, how does the reduced instance look like? Okay, so let's look at the reduction rules first. Yeah, so what is RR1? It says that delete all the vertices of degree 0. That means if there is an isolated vertex, you delete it. So in this case, there are no isolated vertices, so it does not apply. So what is RR2? If G contains an edge UV, so that neighborhood of U is equal to the neighborhood of V. When you contract UV, if UV was an isolated edge, then you decrease K by 1. So I'll write it down. So what is so RR1 I will write down, but it is not applicable in this case. So first reduction rule is this. Delete all vertices of degree 0. The reduction rule 2 is the following, that if G contains an edge UV with closed neighborhood of U being same as the closed neighborhood of V, then you contract UV. What is contraction? We'll see. If UV was an isolated edge, then reduce K by 1. Decrease K by 1. So that's all. These are the 2 rules. So let us number. So what is closed neighborhood? So let us say I call these vertices. I'll number these vertices. So what is the closed neighborhood of a vertex? It is all the neighbors of this vertex, including itself. Okay. So for example, what is the closed neighborhood of 1?
1 and 2.
Correct. Closed neighborhood of 2 is also 1 and 2. So this is an edge for which neighborhood of U is same as neighborhood of V. So we will contract this. So we'll make it one vertex. So we'll say that this is contracted to one vertex and we'll call it 1, 2. And because it is an isolated vertex, so we'll update K by decreasing it by 1. So now, is there any other edge where we can apply this reduction rule to? Okay, now another important thing is once this contraction of edge 1, 2 is done, now this has become a vertex, a single vertex, and we must delete all vertices which are isolated. So we'll delete this. That is
So like
applicable. The
6, 7, 8. So like the neighborhood of 6, no, the neighborhood of 7 and the neighborhood of 8 is same.
correct, correct. So what is the neighborhood of 7?
7 and 7, 6 and 8.
And similarly, 8 also has the same neighborhood. So we can contract 7 and 8. So what happens when 7 and 8 are contacted? So this becomes one large vertex, one super vertex, and 6 is connected to it. So what I'll do, I'll draw a picture. So after what you said, after that we have a picture like this. This is 7, 8. And are we going to update the parameter?
Yes, the value of A will become 2 now.
No, so that is not the rule. The rule is if the vertex edge that you are contracting is an isolated edge. What is an isolated edge? Isolated means one is U is connected to V, but U and V both have degree 1. Then it is an isolated edge. But 7 and 8 both have degree 2. So 7, 8 is not an isolated edge.
Yes, yes,
Therefore, we will not be able to update K.
yes, yes.
So this is all we have. I don't see any other reduction possible.
No, not possible.
Sir, can we
Can you go back?
contract the 7 and 8? Excuse me, sir.
Yes.
Sir, actually, we need to find the closed neighborhood of 7 and 8. In that case, it will include the 7 itself, na, sir.
Yes,
So,
correct.
so it will contain 7 comma 6 for neighborhood of 7, and for 8 it will be 6 comma 8, as it is a closed neighborhood, na, sir.
Yes, yes, yes. So that is what we have done. So what is the closed neighborhood of 7? 7 itself, and it is
And
connected to
6 and
6, 8 also.
oh, okay.
So 6 also, 8 also, and neighborhood of 8 will contain 8 itself and whoever 8 is connected to, that is 6 and 7.
Okay.
So both these neighborhoods are same. So these two sets are same, 6, 7, 8. And that is why we are going to contract this edge, as you pointed out, or Mr. Goel pointed out. So after contracting 7 and 8, this becomes a large vertex like this.
Okay.
Now 7 is connected to 6, 8 is also connected to 6. So therefore this super vertex, which is a combination of 7 and 8, is connected with a single edge like this, 2, 6. So this is the final graph after applying these reductions. So at this point, do you see an edge where one of these two reduction rules may be applicable?
No, I think it's not.
Yeah, I think if you can check that. So what is the closed neighborhood of C? It is 3 itself and 4. I'm looking at this picture. What is the closed neighborhood of 4? 4 itself, 3, 5, 6. Closed neighborhood of 5, 5 itself, 4 and 6. Closed neighborhood of 6, 6 itself, and 4 and 7, 8 together is a vertex. And what is the closed neighborhood of 7, 8? That is 7, 8 itself and 6. So there is no neighborhood which is identical to another neighborhood. I hope that I have written everything correctly.
Yes, yes.
So now at this point, we'll say that we are exhausted. the rules. Let's go back to the question. So accepted answer is 5. So 1, 2, 3, 4, 5 vertices we have got. What is happening to my screen? Okay. So finally, in a reduced graph, we have only 5 vertices. So there's some lag. Okay, so this is the end of it. So for your information, I'm going to organize a workshop on geometric algorithms. So we have prepared a website. I'll show you that website. So you can find more details about this workshop in this website. And if you're interested, you can participate in this workshop. So this is going to give you an introduction to the area of geometric algorithms. Okay, I have to write down the full thing. I think I should have written it before, but yeah, it will take 1 minute maybe. Okay, youtube.com/. So I will also upload this video on YouTube, and you can check the link to my website to this to the website of this workshop. So it's called Joy of Geometry. I think I have written correctly. Yeah. So are you able to see the website?
Yes.
Yeah, so as you can see, this website is going to be 5-day from this Friday to Tuesday. And I think this will not conflict with your usual work timings. So the goal of this workshop is to provide you an introduction to the wonderful field of geometric algorithms. So I will encourage you to participate in this workshop. And the schedule, you can take a look at it. Every day it is starting from 5, except on Sunday, it's a morning session. So I will share with you the link to this workshop in YouTube. Okay. If you have any doubts, you can mail me. This is my email ID, siddharthas1@iic.ac.in. All right. So I think that's all I had for you today. Okay, then. If you have no other questions, we can stop today.
Thank you very much.